Hello friends, in this video we're going to discuss about bra-ket. So what's ket vector, bra vector, and that means Dirac notation. Okay, so this is another lecture of quantum mechanics, so hope you're going to enjoy it. And before we start, please subscribe the channel, hit the thumbs up button, also share with your friends. It's for me to create new contents for you. So let's start. And one more thing, if you want to follow me on Insta, this is my Insta ID. This is my Insta ID, Ozaloikaji 123. So this is my Insta ID, so do follow me on Insta. So now let's start. So now you see, before I explain what is the Dirac notation, explain about Dirac notation. So now you see, in classical mechanics, suppose this is the three-dimensional space. If you have a particle or any other object, if you know the coordinates of this object, then you can study its motion. Okay, what will be the velocity along x-axis, along y-axis, z-axis, what going to be its acceleration, and if you know the coordinates, and you can determine the position vector as well, right? That position vector is going to be, if this is the coordinate, then it's going to be xi cap plus yz cap plus z k cap, right? So in quantum mechanics, particles like electrons, protons, okay, so in order to get their informations in quantum mechanics, so when we deal with very small particles, microscopic particles, so the complete informations of those particles are obtained from the wave function associated with the wave associated with those particles. Okay, that those waves are given by this wave function, and from this function we can obtain all the informations of the small particles, microscopic particles in quantum mechanics. And so in case of classical mechanics, if you know the position, if you know the coordinates and its position vector, you can you can calculate its velocity, momentum, etc., acceleration. Okay, and you can represent its position by a position vector. Similarly, in quantum mechanics also, we used to represent this in the form of a vector. That is nothing but, here we don't use to write the arrow on it. So here, instead of that, we used to write ket. This is called ket vector, ket vector psi. So here, and you see, this wave function is nothing but, it is a complex number. It is a complex function. Okay, complex. It is complex. So its complex conjugate is represented by psi star, right? So in this case also, in Dirac notation, we used to write the conjugate in this way using bra. This is called bra. Okay, this is bra notation, and this is nothing but the conjugate of this, right? So hope you get the idea of the bra-ket notations, bra vectors, ket vectors. Okay, so this is nothing but vector representation of wave function, representing which gives the complete information of particles like electrons, protons, very small particles. So that's how we used to deal with those things, those microscopic particles in quantum mechanics, right? So now let me clean this space first, and let me add one more thing. As you see, this vector represents the position of a particle in space, 3D space, in three-dimensional space, and this vector is for infinite number of dimensions, infinite dimensional space, you can say like that. That is Hilbert space, that we have already discussed in the last lecture. Description in the description box, I have given the link. Do watch that video first. Get the information of Hilbert space, linear vector space first, then you're gonna understand better. Okay, So now, and this word bra-ket, it comes from the word bracket. So from bracket, first three letters taken bra, and next right hand side, on the right hand side, three letters beyond C taken as a cat. Okay, so now let's discuss the properties of brackets. Okay, so before that, let me tell you one more thing. Here you see, suppose we have two wave functions, psi of x and phi and psi of x. Okay, these two are wave functions. The scalar product of these two is represented by phi and psi using bracket notation, right? So this is given by integration. So when you take the function which is in bra, we should take the conjugate of that. Okay, and phi of x dx. So that's how we used to get the scalar product, right? Now let me write the properties of brackets. So now you see, every ket has a corresponding bra, corresponding bra. Similarly, every bra has corresponding ket. Okay, so this is ket vector psi, then its corresponding bra vector is this bra vector psi. Okay, and this is nothing but bra vector psi is nothing but complex conjugate of ket psi, right? It's complex conjugate of ket psi. That's it, right? So similarly, suppose if this is a linear combination of this is suppose linear combination of this A psi 1 plus B psi 2, ket vector psi 2, right? Then so we're gonna have a corresponding combination A star, which is complex conjugate of A bra psi 1 plus B star bra psi 2, right? So this is the corresponding bra of this ket, right? So now let me go to the next property. So just wait, let me clean these things. Let me do one thing, let me take a new slide. Okay, so here is the new slide. So next property is the properties of scalar product. So scalar product, so let me write here properties of scalar product. So now you see, so scalar product of two functions phi and psi, if you take its conjugate, then you're gonna get the scalar product of psi and phi. Okay, the complex conjugate of scalar product of phi and psi, its complex conjugate is equal to the scalar product of psi and phi, right? So it is not like this kind of vectors where you see the scalar product of A vector and B vector is equal to B dot A. So here this logic is not applicable. Okay, remember that. So now you see one more thing. First let me show you how. Okay, So by definition we know that dot product of this is given by integration phi star psi dx, right? Just we have already got this one, right? I have already given shown this one scalar product of two functions, right? Psi star phi phi star psi dx. So I have not written the x here, okay? So hope you have understood this. So now you see, if you take the complex conjugate of this left hand side, then you have to take that on right hand side as well. And if you do so, now you see, suppose we have a complex number a plus ib, its complex conjugate is a minus ib. Then if you take the complex conjugate again, then you're gonna get again a plus ib. So that's why we have complex conjugate of phi here. So if you take again complex conjugate, you're gonna get phi, right? So you're gonna get phi. So what we can write here, phi, but here there is no conjugate, so it's gonna be psi conjugate dx, right? So hope you have understood this. So if that is the case, then you can rearrange that this way, right? Dx, and this is nothing but dot product of psi and phi, a scalar product of phi and psi. So this is the property. So hope you have understood this, right? Now you see, so let me clean this part, take the screenshot. So just let me go to a new slide. Okay, just wait. Now you see, suppose we have phi dot product of phi and another function which is in the form of linear combination a1. So let me write this way. Okay, let me take the scalar product of phi and psi. Okay. If this psi is, suppose this psi is equal to a psi 1, this ket psi is, suppose a psi 1 ket plus b psi 2, ket vector psi 2, then it can be written this way, phi, then here we can write this, right? Just wait. We can write this way. So now what going to be the result here? So a can be taken out. This is some scalar, right? Scalar, it doesn't mean that it may always going to be a real number, it may be complex number. Okay, so now you see, we can write scalar product of phi and psi 1 plus b scalar product of phi and psi 2, this one with this and this one with this, right? So hope you have understood this. We can write this way. Okay, now you see, what if phi is equal to a phi 1 plus this ket phi plus b ket phi 2. Okay, in that case we can write this one like this, a phi 1 plus b phi 2 here psi. Okay, so how to write this one? So this is, in this case, what we can write here. Now if we use this property that scalar product of phi and psi, its conjugate is scalar product of psi and phi, right? If we use this property here, so then what we can write is complex conjugate of scalar product of phi and a scalar product of psi and a into phi 1 plus b into phi 2. So here if we take complex conjugate, then this order will be reversed, right, according to this property, right? So hope you have understood this. And if that is the case, then again perform the scalar product this way as we have done above. So similarly a, and first thing is now psi. So as we have star here, so star, then psi and phi 1 star complex conjugate, then again b star complex conjugate of b, then here psi and phi 2, it's complex conjugate. Then again use this property, then you can reverse the order removing the star, right? A star, you can write phi 1 psi plus b star, and if you remove the star, then phi 2 psi. That's what you will have, right? This is another property. So hope you have understood this. Now what if we take the scalar product of this one and this one, right? Then how to write that? Suppose we let me write phi instead of phi a instead of psi, let me write a psi 1 plus b psi 2, and instead of phi, as we have already taken a and b here, so a and b already taken here with phi psi 1 and psi 2. So with phi, let me take other scalars. Suppose let me take c and d, c phi 1 plus c phi 2, d phi 2, let me take that. Okay, so what going to be the result here in this case? So here you see, now in order to get the scalar product of these two, just compare this one and this one with this first. Okay, let me take this way, just wait. So first take this one. So what gonna be its result if you use this result? Okay, so here what happens, this a becomes a star here, then phi 1 psi, here we have psi 1 and phi 1. So if you use that result, then what you're gonna have here, so here what we have to take this a star, then this coefficient also should be written outside, but here we don't know, we are not going to put star here. Okay, so star will be on this coefficient. Okay, as you can see here we have the coefficient a, and here we have put star. Okay, now that means you can consider this way, that in place of psi we have now this one c phi 1, and in place of f phi 1 we have a psi 1. Okay, then you can use this result. Okay, so hope you have understood this. So here we have written as, in addition to that, this scalar should be written outside, then scalar product of phi 1 and psi 1 and phi 1. Okay, then again now use this result. So here b star, then this scalar again comes out c, then phi 2 and psi 2 and phi 1, right? Now let us take this this part with this one. Okay, now let me replace this one by d phi 2, then again use this result. You can have plus, this is not completed yet, okay, so plus A star D psi 1 and phi 2. Now it's done. This is phi 1 phi 2, okay. Then again B star, then D comes out, then we have phi 2 psi 2 phi 2 psi 2 and phi 2. So this is the complete result from here to there, right? So hope you have understood this. So just take the screenshot, or you can pause the video to note it down, okay. So now let's discuss and some other properties as well. Now next property is, so in for any state and for any vector state, for any vector, state vector, we used to say state vector, ket psi of Hilbert space H, let me just write this way. This is always real positive, is always real and positive, and it's going to be equal to 0. It's going to be equal to 0 if it is this ket vector psi is 0, okay. And we're going to say it is normalized, this state is normalized if this is equal to 1, right? So now let's discuss about two important inequalities. One is source inequality, source inequality. So for any two states, suppose we have ket psi and ket phi, okay, the mod of square of the mod of scalar product of psi and phi, that is always less than equal to scalar product of psi and psi and that of phi and phi, right? This is one inequality, and another is triangle inequality. So let me write this one. Well, sir, inequality is triangle inequality. So that is nothing but square root of scalar product of sum of psi and phi and that of again psi and phi is also less than equal to this. Plus square root of phi and phi, okay. So this is also this is known as triangular inequality, okay. So remember these properties, okay. Now let us discuss about orthogonal states, okay. Let me clean this first, just wait, let me clean this things. So orthogonal states, orthogonal means these two vectors must be perpendicular, ket phi and ket psi, okay, and they are said to be orthogonal if the scalar product of phi and psi is equal to 0, then or you can write this one, are said to be orthogonal. if this is equal to 0, right? So as in case of in general vectors that we used to know, a dot b is 0 means these two are perpendicular. Similarly, scalar product of phi and psi are 0, then they are orthogonal. Okay, and one more thing is orthonormal. So for this case, it must satisfy the condition of orthogonal, perpendicular, and it must satisfy the normalized condition also. This must be equal to 1 and this must be also equal to 1. These two functions must satisfy the normalized condition as well as orthogonal condition, then these two functions are said to be orthonormal. So hope you have understood this. Now let us take some questions, examples, so that these things becomes more clear to you. So how to find the scalar product and all these things that we have discussed till now. So let's take the first question here. So here what we need to find, this here ket psi is given and ket phi is given. We need to first question, we need to find bra of phi. So how to find it? First let me solve this one. So bra phi is nothing but the conjugate, complex conjugate of ket phi. As it is in matrix form, we need to find the transpose of this ket vector psi, and then we need to take the complex conjugate. So if you transpose this, if you take the transpose of this ket vector phi, if you take the transpose, okay, then it gonna be this column matrix becomes row matrix 2 minus I and 2 minus 3i, and if you take the complex conjugate, then it gonna be 2 minus I becomes plus I and 2 plus 3i. So this is what? This is the bra phi, right? So hope you have understood this. So that's why if we use this symbol dagger, then it will be more suitable. This is called dagger symbol. It represents transpose as well as complex conjugate. Okay, we used to represent first we need to take the transpose, then we take the conjugate. So to represent this operation, we use this symbol, which is dagger symbol. This is called dagger symbol, right? So now you see, next one, evaluate the scalar product, this one. Okay. So how to find that? So here ket phi and bra psi. So how to do that? So next one, this first one we have done. This is suppose first one. Now let's find the second one, number 2. Scalar product of phi and psi, and we have got bra phi is this one, right? Take the row matrix 2i 2 plus 3i, okay, and let me take the column matrix, okay, that is ket psi, that is minus 3i 2 plus I, then 4. Okay, so how to do that? This is very simple, right? So first element of the column, first element of the first element of the row, first element of the column, right? Just wait, let me find some space here. Okay. So that is 2 into minus 3i, then plus, then second element of the row, then second element of the column, that is 2 plus I, then again third one of the row, then third one of the column into 4, right? So hope you have understood this. So now let's multiply and simplify this, and then what we're gonna have, just wait. So now you can see this is I. If we multiply this, this become minus 6i, then plus 2i, then minus 1, then 8 plus 12i. So this is going to give you 8 minus 1 is 7, then 12 minus 6 is 6, 6 plus 2 is 8, so it becomes 8i. 7 plus 8i, this is the result, right? So hope you have understood this. Now let us take another question. Okay, take the screenshot. Okay, and one more thing, let me go back to previous slide, just wait, where I have explained these things. So here, this one, here you can see this one I have written. So use, instead of star, use dagger symbol. Okay, use dagger symbol. So as we need to transpose, and then we need to take the complex conjugate, so to represent them, use the dagger symbol. Okay, so hope you have understood this. So here you see there's state vectors are given. Ket phi is given by this. Okay, then ket chi is given by this. Okay, so we need to calculate this too. Okay, first let me calculate ket of phi and chi, phi plus chi. Okay, so here you see this is nothing but equal to ket phi plus ket chi, and let us use these values, use these combinations here. Those are given in the question. So that is 3i cap, sorry, 3i, not cap, this is I complex one, that imaginary number. Okay, then phi, ket phi minus 7i ket phi 2. Okay, then for this one, what we have, this, that is minus ket phi 1, then plus 2i ket phi 2. Right, very simple. So hope you have understood this. Now simplify this two, then it's gonna be 2i ket phi 1, then this two, you're gonna get minus 5i ket phi 2. That's it, right? Hope you have understood this. Now you see, sorry, I made a mistake here. This is 3i, this is not 3i, there is 1, nothing means 1. So this one not gonna be equal to 2i, this is gonna be minus 1 plus 3i. Okay, minus 1 plus 3i. So from these two, here you see, this is, if this is minus I, then you can write here 2i after subtracting this one from this one. So now you cannot do that because there is no I. Okay, so hope you have understood this. This is the result. Now we need to find the bra of sum of these two vectors, phi and chi, sorry, psi and chi. So how to do that? So this is nothing but complex conjugate of this, right? So let's take the complex conjugate of this one. So then minus 1 plus 3i, its complex conjugate, and its complex conjugate gonna be equal to phi 1, right? Bra phi. Okay, it's complex conjugate. So that means you have to take the transpose, and then you have to take the complex conjugate. So you can simply, you can write, if you write this one is equal to this one, then also it is correct. Okay, so but when we use dagger, then it becomes more precise. Okay, so now minus again 5i, its complex conjugate, then complex conjugate of this one, it should be this bra phi 2. Okay, then complex conjugate of this one will be minus 1 minus 3i, then complex conjugate of this, it's become minus 5i, so minus minus plus 5i bra phi 2. So hope you have understood this, right? So this is the result we have got. Okay. So now let's solve this one. Scalar product of this thing. So let's find the scalar product. So pause the video and note it down. Let me clean this first. Okay. Now let's find scalar product of phi and chi. So it's psi and chi. Okay. So how to find that? So scalar product of so here you see we have here, this is ket psi is this one, so that's why bra psi will be complex conjugate of this, complex conjugate of this ket psi, right? Then that's gonna be equal to, if you take the complex conjugate of this one, then what you gonna get? This 3i will be minus 3i, then it's gonna be bra phi 1, then this minus 7i, that's gonna be plus 7i after taking complex conjugate, and it's gonna be bra phi 2, right? This one, then into ket chi is this one. Okay, so let's use this value here, minus ket phi 1 plus 2 ket phi 2, right? So now let's multiply these two. How to do that? So minus 3i into minus 1, here there is minus sign, so into minus 1, then bra phi 1 ket phi 1, then plus minus 3i into 2i, then bra phi 1 ket phi 2. We have done this one with this one and this one, and now let's multiply this one with this one and this one, right? Then plus 7i into minus 1 bra phi 2 ket phi 1, then plus 7i into 2i, then bra phi 2 ket phi 2. That's what we have got. Now you see, since these two are orthonormal, these two vectors are orthonormal, so therefore they must satisfy the orthogonal condition, right? So their scalar product must be equal to 0. That means scalar product of phi 1 and phi 2 is equal to that should be equal to 0. Similarly, phi 2 and phi 1 must be also 0, and they must also satisfy the normalized condition, that is phi 1 and phi 1, that should be 1. Okay, and that this phi 2 and phi 2, that should be also equal to 1. Okay, bracket of phi 2 and phi 2, that should be also equal to 1. If that is the case, this 2 becomes 1 and these two terms becomes 0. So we left with, if you multiply this two, then you're gonna get 3i, and if you multiply this two, then you're gonna get minus 14, right? So this is the result we have got. So this is what scalar product of phi and chi we have got. So now let me copy this result. Let me go to the next slide. So here is the result we have got, which can be written as minus 14 plus i3. So now we are to find scalar product of this, sorry, not this one, this one, that is scalar product of chi and phi in reverse order. So So this must be equal to the complex conjugate of this, right? We have already got this property, right? If that is the case, take the complex conjugate of this one. That's going to be minus 14 minus I3. That's it. So hope you have understood this. So thank you for watching this video. See you in the next video. Okay, stay connected.